All right, in the last lecture we looked at the general case and developing a concept where we could calculate the magnitude and phase for the general case of a transfer function representing our system and for a specific frequency. Let's look at an example. Example is a little bit easier than our general case. So let's imagine a transfer function, a system that be represented by 10, s plus 5, s plus 2, and s plus 3. Okay, just a generic transfer function that we want to find the magnitude and phase at a specific frequency. So let's let the omega equal 4 radians per second. Okay, so that's what we want to do. So if we do our substitution first, for j, we're going to put our frequency in for our s. What we end up with is 10 4j plus 5 divided by 4j plus 2 and 4j plus 3. All right, so now we have our equation that we want to solve and find the magnitude of g at this specific frequency. Magnitude and phase, I'm sorry. But we're going to do this in parts. So if we look at just the magnitude of this, 4j, sorry, that's a little sloppy there. What we're going to do to calculate the magnitude is calculate the we're going to calculate the magnitude for each of these. Magnitude of this, magnitude of this, magnitude of this, and the magnitude, we're just going to use the Pythagorean theorem. Okay, so what we're going to end up with then is 10, and the Pythagorean theorem, we're going to end up with our complex part squared plus our real part squared, sum of those, and square root. So it's going to be square root of 4 squared plus 5 squared, square root. Okay, and then and that's going to be over this radical 4 squared plus 2 squared square root, and that's going to be times 4 squared plus 3 squared square root. Okay, and we work all of that out, and we end up with 2.86 as the value for that. All right, so this is what I'm going to call the raw magnitude. All right, now this is and one thing I didn't mention, and I should have, is we're looking at the relationship between the input and the output, right? And that is what our transfer function is the output divided by the input. And so in this case, this magnitude ratio that we get in here is a magnitude ratio. It's the ratio between the input and the output of our system. So we feed a sine wave in of unity magnitude, or a magnitude of 1. What we will get out is a sine wave of the same frequency with a magnitude of 2.86. So make a little, do this like this. Our input is here, and if this has a magnitude of 1, let's say, then our output would be shifted in phase, probably same frequency, and would have a magnitude here of 2.86. Okay, so this just it is the ratio of the input to the output. Now, here comes some funkiness. All right. So this makes perfect good sense to me, and I hope it makes perfectly good sense to you. But this isn't how we do it for the Bode plot. The Bode plot, we don't use a raw magnitude. We use a magnitude reflected in decibel or dB. All right. Yeah, I don't know. The electricals, you know them. So we have the 4J, and if we represent this in decibels, and decibels was developed associated with the communication industry again, and the definition of a decibel is 20 log times the value of the magnitude ratio, okay, the raw value. And so in our case, it's going to be 20 log of 2.86, okay? And that equals 9.14. Okay? So this would be the magnitude ratio in dB. All right. So now this is actually what we would plot, and I haven't talked about this, but when we're plotting our Bode plot, and we're plotting the magnitude plot of that, the scale here is actually dB. Okay? That's plotted in dB. Now, another thing I haven't mentioned is that the frequency is a log scale. This is log scale. So we've got a log scale on our horizontal axis, representing our frequency, and our vertical axis is dB. Now, on our phase, it's in degrees, and again, it's the log scale of the frequency. So this is specific. This is how the Bode plot is set up, and so we have this would be our magnitude ratio for our Bode plot. So if we were wanting to plot this, we would come out here to omega equal 4, and we would come up here to 9.14, and we would plot that point in there on our magnitude plot. Okay, so we would have 1 point on our magnitude. Now, what do we do about the phase? Okay, well, the phase is we're going to calculate, and we're going to say the angle of J4 is equal to. Now, what we're going to do is we're going to sum the angles for all the zeros and then subtract all the angles for the poles. Okay, so in this case, the angle for the 0 can be represented by the tangent, the arctangent of 4/5. Okay, and this is our sine over cosine, our vertical minus or over our horizontal, however you want to think about it. It's just some simple trig in there. We're just calculating the angle in there of our complex vector. And so we only have one 0, so we only have one sum, and then we're going to start subtracting off the angles for the poles. And that's going to be 4/2 for the first one, minus tangent, arctangent of 4/3 for the second pole in there. And we work that out, and we end up with a minus 77.9 degrees on that. And so here on our plot, what we would end up doing is here at the omega equal 4, this is 0, we would end up going down here to minus 77.9 and plotting a point in here on phase. Okay? Now, you can verify this in MATLAB by coming in here and using a command, and I ask you to do this on the homework, a mag phase omega out. Okay, it's going to give you 3 arguments out for this input Bode of G omega. So what you're going to put in here is your transfer function, and you'll probably establish your transfer function up here. G is equal to TF of whatever, and establish your transfer function, and then the frequency you want this evaluated at, and as a result, it'll pop out your magnitude, your phase, and the omega out. In this case, we have a linear system, so our omega out and our omega in should equal each other, and but you'll get a magnitude and phase. Now, be careful. This magnitude is not in dB, and so in order to convert it to dB to check your answers, you have to do, there's a command in there, let's see, something like mag to dB, something like that, and of a value, and so in this case the magnitude would go in here, and that would give you an output of the magnitude in dB, so you can check that against your answers. Okay, so that's how we run through and calculate the magnitude and the phase of a transfer function for a specific frequency, and we want to make sure the phase is in dB, and with that we could plot 2 points, and then once we get those 2 points, our magnitude and our phase points for that specific frequency, then we turn around and we do it for thousands of other points and create our Bode plot for it. But actually we'll learn to sketch it, and we'll learn to ask MATLAB about how we do that. But that's the process that we want to go through for calculating the magnitude and phase.